Module 12, Introduction, Formal Charge and Resonance. Formal charge and resonance will be used in conjunction with Lewis diagrams to help provide the best possible representation of bonding in a molecule or molecular ion. Formal charge is assigned to an atom in a molecule and assumes equal sharing of electrons between bonded atoms. Formal charge is going to be calculated in this way. We'll take the group number associated with the individual atom. We'll get that right off the periodic table. We'll subtract from that the sum of the number of electrons in electron pairs and the number of bond lines drawn to the individual atoms. Let's consider a Lewis diagram associated with ozone. So we've ratcheted through our 5-step algorithm associated with the construction of the Lewis diagram, and here's a representation that we might have come up with. Let's take and assign a formal charge to each of these 3 oxygens using this particular formula. So oxygen is in group 6, so we'll take 6. Number of electrons in electron pairs from the standpoint of this oxygen, that's 1, 2, 3, 4. There are 2 bond lines drawn to that oxygen. I do that arithmetic. I see the formal charge associated with this oxygen is 0. I apply the same formula to this oxygen. I'll see its formal charge is +1. Here, formal charge of -1. How are these formal charges used? Well, to begin with, the sum of the formal charges in a molecule or molecular ion is equal to the overall charge. So for a neutral molecule like ozone, the sum of those formal charges would be 0. If it is a polyatomic ion, the sum of the formal charges is the charge on that ion. The most energetically favorable diagrams tend to have atoms with formal charges as close to 0 as possible. If we look at our representation of ozone, this is a neutral molecule. Indeed, when I sum 0 plus 1 minus 1, I get 0 for that neutral molecule. I'll use formal charge in conjunction with resonance. So resonance is a way of describing the delocalization of electrons within a molecule or molecular ion. We're often concerned with what we'll call resonance contributors. These will differ only in the positions of electrons within the Lewis diagram. So in constructing Lewis diagrams for a molecule that exhibits resonance, we're often concerned with the major contributor. This will be the diagram that represents lowest energy or the most stable arrangement of those electrons and bonds within the molecule. Right, we'll determine that major contributor using these prioritized criteria. We'll look to maximize the number of atoms with full octets. We'll want to have those formal charges as close to 0 as possible. When they cannot all be 0, we will want to assign negative formal charge to more electronegative atoms. We'll maximize the number of covalent bonds within our diagram, and we'll try to minimize the number of unpaired electrons. Let's take and apply those criteria and come up with a Lewis diagram for, let's try carbon dioxide. Well, if I consider carbon dioxide, I want to come up with that Lewis diagram. Step 1, recall, we would determine the number of valence electrons. Right, carbon in group 4. I've got 2 oxygens, each in group 6. I do that arithmetic, I'll see that I have 16 valence electrons. I'll put the carbon atom in the middle. I'll attach the oxygens. Give everything an octet that needs an octet. Here, carbon and oxygen will require an octet of electrons. So I've satisfied the octet rule. I now do the electron accounting, and I recognize in this Lewis diagram, I have used 20 valence electrons. I had but only 16. Okay, we've seen this before. We'll take a lone pair off the central atom, a lone pair off an adjacent atom, and I'll introduce a double bond between the 2. In doing this, I've now used 2 fewer valence electrons while still satisfying the octet rule. Okay, I do the accounting again. I recognize I'm using too many. This diagram is using 18 valence electrons. I had only 16, so I'll repeat that process. I'll take a lone pair off the oxygen. I'll take a lone pair off the carbon. I'll introduce a double bond. Okay, let's take and calculate the formal charges associated with those three different atoms. So if I look from the standpoint of this particular oxygen, that is in group 6, I have 4 electrons in lone pairs of electrons. I have 2 bond lines drawn to that particular oxygen. The formal charge there is 0. Do the same thing for this carbon. Carbon is in group 4. There are no electrons in electron pairs. I count 4 bond lines. The formal charge associated with that carbon is 0. This oxygen has the same arrangement of lone pairs of electrons and bonds as this oxygen did, and indeed its formal charge is 0. There's another way I could have arranged these bonds and lone pairs of electrons and still satisfied the octet rule. Let's take a look at what that particular Lewis diagram would have been. Imagine I had oxygen triple bonded and oxygen singly bonded to that central carbon. I'm still satisfying the octet rule for all 3 of the atoms. I'm still utilizing only 16 valence electrons. Let's calculate the formal charges that we see associated with that particular arrangement. Carbon, still 0. This particular oxygen would have had 6 minus the sum of 6 plus 1. That would be minus 1. Here, before I even do the necessary arithmetic, I realize this must be plus 1, since the sum of the formal charges would need to be 0 for this neutral molecule. And I could just as easily have drawn that triple bond to this other oxygen. Of course, the formal charges now would be plus 1, 0, and minus 1. In trying to decide between the 3 forms represented here, this, and this, which is the major contributor, well, we would say this particular arrangement represents lower energy and greater stability. What is the actual arrangement of the electrons within carbon dioxide? Well, it's a combination of what we see here in what we would call the resonance hybrid. This contributes much more to that resonance hybrid than either of these forms would, because the formal charges here are all 0. Now, it's a common misconception. Many people would consider that somehow the carbon dioxide is oscillating between these 3 different arrangements. That's not the case at all. It's not transient states of the molecule. There is one arrangement, one delocalization of electrons within carbon dioxide that is the resonance hybrid. These are representations of the contributors to that resonance hybrid. Let's try one more. Let's do thionyl chloride. This would have formula SOCl2. So again, we'll start by identifying how many valence electrons do we have. All right, I've got 2 atoms from group 6. So 2 times 6, I've got 2 from group 7, 2 times 7. I do this arithmetic, I'm going to have 12 plus 14 for 26 valence electrons. Sulfur is least electronegative, so I will stick it in the middle. I'll attach the adjacent atoms. I'll give everything an octet that needs an octet. Here, all of these atoms would require an octet. Satisfy the octet rule for all 4 of the atoms. I now check the accounting. How many valence electrons have I used? Or from the standpoint of each of those adjacent atoms, there's 8, 16, 24, plus the 2 more, 26. Indeed, I had 26 available, so I would consider this to be a Lewis diagram associated with thionyl chloride. If we go through, check the formal charges. All right, well, from the standpoint of this, that's in group 7. I'm going to subtract away from that the sum of 6 plus 1, that is 7, so the formal charge here is 0. Formal charge here, also 0. Apply the same formula to that particular oxygen, I'm going to get minus 1. Apply the formula to this sulfur, I get plus 1. Again, the formal charges do indeed all sum to 0. Well, I recognize I've got some non-zero formal charges here. Is there a way that I could have shifted some of the electrons represented here and reduce those formal charges? So unlike what I was doing to try to use fewer valence electrons, where I was removing lone pairs of electrons from a central atom and adjacent atom, I'm not doing that here. I'm simply wanting to shift electrons from perhaps a lone pair position into a bonding position. Let's take and consider this arrangement. I still have chlorine. The chlorine. Chlorines were okay, right? Their formal charges were 0. But let's imagine I took and shifted a lone pair of electrons from this oxygen into a bonding position. Still using 26 valence electrons. Everything that needs an octet has an octet. I'm violating the octet rule for sulfur, but sulfur is in period 3 on the periodic table. It can have an expanded octet. If I went through and calculated the formal charges in this particular arrangement, here we're still 0, 0. This oxygen in group 6, so 6 minus the sum of 4 plus 2, that is 0. Here the same thing. 6 minus the sum of 2 plus 4, that is 0. I would consider this to be the major contributor to the resonance hybrid associated with thionyl chloride. So master formal charge and resonance by completing the exercises associated with Module 12.